In this video, we're going to look at energy and simple harmonic motion. And the definition of elastic potential energy is the elastic potential energy is 1/2 kx squared. Now, in our class, we use a U instead of a PA. Our textbook uses a PE, but we use a capital U to show potential energy of a spring. This W elastic is the work done on an elastic object like a spring. We know that work is force times distance, which we also know is equal to the change in potential energy, which is 1/2 kx plus 1/2 kx minus that 1/2 kx minus 1/2 kx to make sure it's in the same direction. But anyway, when you get down to it, it's 1/2 kx squared minus 1/2 kx squared. The work that we would do on a spring is equal to the change in the elastic potential energy. Here is the total mechanical energy that we will come across. Total mechanical energy that we've studied so far is 1/2 mv squared is the translational kinetic energy, 1/2 I omega squared is the rotational kinetic energy, mgh is the gravitational potential energy, and 1/2 kx squared is the elastic potential energy. That's our new potential energy. So now we have a new energy that when we deal with conservation of energy that we can work with. So here's an example. The figure below shows an object of mass 0.2 kilograms that is vibrating on a horizontal frictionless table. The spring has a spring constant of 545 newtons per meter. It is stretched initially to 4.5 centimeters and then released from rest. Determine the final translational speed, V final, of the object when the final displacement of the spring is 2.25 centimeters and 0 centimeters. So we're going to use conservation of energy to solve this problem. We know that the final energy has to be equal to the initial energy. So we have all these different energies here all listed. Now a lot of them are going to be 0. And so it breaks down to just this. We have kinetic energy and elastic potential energy will equal the elastic potential energy. Because what they're saying here is this new equation that deals with what energies we have. So what we do is we plug in our values. Actually, we could solve for the velocity and then plug in our values because we want to know what the velocity of the object is at 2.25 centimeters. This right here, the initial energy was when you pulled back on the ball and you're about to release it. It didn't have any velocity at all. So that's why it was all potential energy in the spring. It didn't have any height. It didn't have any velocity. So the only energy when you pulled back on the ball was this potential energy in the spring. And that converted into kinetic energy, that translational kinetic energy of the ball moving back and forth, and potential energy in the spring. So you know if you start off with 10 joules of energy in the spring, it just changed back and forth between these two, but they still added up to 10. So we have this equation here that lets us solve for V final. So now we just plug in our x values. And we have our 0.045 meters minus a 0.0225 meters squared. And so part A, you get 2.03 meters per second. And in part B, you end up with 2.35 meters per second. So just to review here, this MGH ended up being 0. There was no rotational kinetic energy, so that was 0. But finally, it did have some velocity, so we did have kinetic energy left over, and it did have some displacement, so we did have potential energy in the spring. And over on the right-hand side, initially it started off from rest, so that right there is 0. The initial velocity was 0. It was not rotating, so this whole rotational kinetic energy was 0. Didn't have any height, so that whole thing was 0. So when you go to 1/2 kx squared, you end up with the only energy that's left initially. Now we're going to do a vertical problem. A 0.2 kilogram ball is attached to a vertical spring. The spring constant of the spring is 28 newtons per meter. The ball is supported initially so that the spring is neither stretched nor compressed as released from rest. So it's right at that equilibrium point. We're not putting a force on the spring. In the absence of air resistance, how far does the ball fall before being brought to a momentary stop by the spring? So again, we're going to do this idea of initial energy equals final energy, and ask yourself, what kind of energy do you have initially? What kind of energy do you have finally? Remember, it comes to a stop at the very bottom. So what you do is you set up your initial, your final energy equals your initial energy, and make all other energy, make any energies that are 0. We'll cancel out, and you're just left with the energies that you have. So I would pause the video and see if you can do that on your own. Okay, here's the original equation. We have all the energies, and then you have to decide which ones are zero. And here we only have, in the beginning, only have gravitational potential energy. It only has height. It has no velocity. And on the bottom, it stops. It has no height. We call that h equals 0. So the only thing that occurs is the potential energy in the spring. So we go ahead and plug in our values, and we end up with a height of 0.14 meters. Now we're going to look at a different kind of motion called the pendulum. A pendulum is just something that moves back and forth. There's a mass on a string that moves back and forth, and we have it moves in simple harmonic motion. It'll form a sine curve or a cosine curve, just like the mass on the spring will. Very similar motions. The equation are very similar as well. Omega is 2 pi f. Now the difference here, though, is that it equals square root of g over L instead of m over k. And so your period equation will be slightly different. And actually, this is the frequency equation. It's 1 over 2 pi times the square root of g over L. Your period equation would be t equals 2 pi times the square root of L over g. So here we have, determine the length of a simple pendulum that will swing back and forth in simple harmonic motion with a period of 1 second. If you could, please pause the video and try this problem. Using our equation, t equals 2 pi times the square root of L over g, we plug in our values and end up with an answer of 0.248 meters. So going back to this slide, it's important to remember that t equals 1 over f. So if we have this f equals 1 over 2 pi times the square root of g over L, since period equals 1 over that, the inverse of that, the period, which is a more common equation, equals 2 pi times L over g square rooted, or to the 1/2. That L is the length of the pendulum, and remember, it's measured from the pivot point down to the center of mass, and g is 9.8. So pendulums are dependent on gravity, where the period of a mass on a spring is dependent on the spring constant and the mass that's attached to that spring. So the mass on a spring can actually work in without gravity, where a pendulum cannot.